If you look at the bird has like distributed sensors on the wing, and also, like sensors on the wing, and also you have maybe eyes and also ears to sense what is happening on its body and also around the environment. And then all the informations are clustered into the brain of the bird. And then the brain of the bird processes this information, think about it, what to do with it, and then the brain thinks, okay, I'm going to do this, and then this decision is given to the muscle of the bird. And then the muscle try to move the wing in a certain way to achieve certain functionalities.
Yeah.
So I am mimicking this function of like feel, think, and act, and to how to design these algorithms to mimic the brain of the bird to achieve these certain functionalities. Yeah.
This is Coffee with Martin. In this episode, we explore a fundamental shift in how we design aerospace structures. What if a wing is no longer something static, but something that can adapt? Not just withstand forces, but respond to them. I'm joined today by Roeland de Breuker, full professor within the Department of Aerospace Sturctures and Materials, and he is also the head of the department. And my second guest is Sherry Wang. She's an assistant professor. Her research interests include nonlinear control, aerial robotics, and active morphing structures. Together we talk about morphing wings, smart control, and adaptive systems. What does it mean when structures begin to sense, process, and react? Because the next step in aviation isn't just building stronger systems, but building systems that can adjust in real time. Let's get into the conversation. So, welcome guys, girls, Sherry, Roeland, on this episode of Coffee with Martin. And my first question is that I ask to every guest is, how do you drink your coffee? And or do you drink coffee? Roeland?
Actually, I don't drink coffee, Martin. I'm just a huge fan of water. So, and I occasionally drink tea, but I never drink coffee.
Yeah.
No certain reason, no health reason. Just I don't drink coffee.
And if you look at your past, did you ever drink coffee or?
Yes, until I was like in my puberty. And then I decided to stop drinking coffee.
Interesting. And for you, Sherry?
I also don't drink coffee, actually. So when I was in China, there was not actually like a coffee culture or something.
No.
So I don't drink it. And then I came here in like 10 years ago. And then I started to drink coffee because I see everyone else was drinking coffee. So I was trying to drink coffee because also like after having lunch, I got very sleepy. So I drink coffee. But I also observe myself have a very deep dive after I drink coffee. So it's a spike of my attention time, but then suddenly it's also a very deep dive. So I quit it after 1 year of trying it. And
now you drink tea or
not just water, also
just
water.
Oh, that's good to hear.
But I really like the smell of the coffee. I like somebody drink coffee around me. The smells very good.
So please keep drinking coffee.
I have my coffee ready on my right side. So the second question I start with is can you introduce yourself in one sentence? If somebody asks you, hey, Roeland, Sherry, what do you do at the TU Delft? So in one sentence.
I'm an assistant professor at TU Delft doing flexible aircraft dynamics and control.
And I'm a professor here at TU Delft, and I'm really interested in how different disciplines work together. Structures, aerodynamics, control, and so on, mainly applied to wings. That's what I really like.
And that's the episode of today. We're going to speak about morphing wings, flexible wings. There's a big project called SmartX. That's correct, right? Mm-hmm. Maybe can one of you introduce that project?
Yeah, I can say a few words about that. It's actually started as a TU Delft internal project. I need to think now, maybe 7 years ago or something. I don't pin me on the number, but and it started as an internal project in ASM, actually, in our department. Where the goal was to a few goals. First, to advance the technology of smart structures. Maybe we can get into what are smart structures later in this episode. And the second goal was also to integrate the department a little bit, because we have different. Our department of Aerospace Sturctures and Materials is quite large. We have 30 plus professors. We have more than 100 PhD candidates, postdocs, many master students, and so on. So we work on different topics. So the goal was a bit to integrate structures, sensing, actuation, smart materials into one vision for the future of commercial aircraft wings.
Yeah.
And then we did a lot of studies of this integration of all these different disciplines. And then we also built our first prototype called the SmartX Alpha wing, which we tested in Delft. And since then, actually, we have spin-offs into also different Dutch national projects, European projects. So then it's really started to grow, and we became known for this type of research.
And the Alpha notification is that then it's the first.
The first. Yes.
And is there also a beta and a gamma?
There's already a beta indeed.
Yeah.
That was actually tested very recently, less than a year ago,
okay.
at DNW, at the German-Dutch wind tunnels in Marknisse here in the Netherlands.
Yeah.
So in a quite large wind tunnel, well large, I mean from our point of view, like it was more than 2 meters diameter. We tested it at 60, 70 meters per second.
Okay.
So that's quite fast, again, from a university point of view. So it was like almost realistic scale of an outboard section of a high aspect ratio wing at
high aspect ratio
high aspect
wing.
ratio,
Yeah.
yes. The aspect ratio is actually a term that we give to a wing, and it determines how slender the wing is essentially. It's essentially the ratio between the surface area and the span.
Yeah.
And let's say the higher the slenderness of the wing, the lower the drag of the wing.
Yeah.
So essentially, we always want to go to more slender wings, longer wings. Of course, then we get into different problems, like weight and loads and so on, aerodynamic loads on the wing. So we cannot continue forever.
No.
But if you look at sailplanes, for instance, they are really, really slender wings, so they're very efficient in drag.
And you said drag, that's the main goal, to lower that drag coefficient.
Correct.
Yeah. And what was your role as Roeland in the whole project? What part of the project did you contribute on?
My contribution was, together with some other colleagues, we thought of set up the initial project, SmartX, and then I was also the supervisor of 2 of the PhD candidates that were initially hired on the project, and I could also put my passion in the wing. Part of the research was also dedicated to morphing, which is really
maybe we should ring the bell as well. Morphing.
That's actually an interesting question, Martin, because morphing, there's no, let's say, unique definition of morphing. So you have different institutes worldwide working on the topic, and people might have different definitions. So what I'm going to say now is
your definition.
My definition of morphing. But morphing is essentially, again, if you look at the wing, it's a continuous shape change of the wing. That because at the moment wings have a lot of elements like control surfaces which make the aircraft roll and pitch and so on, but they're typically discontinuous from the main structure. And what we're trying to do is to integrate all this functionality into the wing, into one continuous system, essentially. And so it's essentially it's a continuously deforming structure, if I can call it like that.
Okay. And Sherry, you also worked in the project?
Yeah.
What was your role, or what is your expertise you brought into the project?
So I had the honor to contribute to the project while my colleagues works on the hardwares to how to make the wing morph, so make the wing can morph. I'm working on a very complementary research area that mimics the brain of the bird to make the wing morph in a smart way.
Can you explain that? That's interesting.
Yeah, so if you look at the bird has like distributed sensors on the wing. And also, I mean, like sensors on the wing, and also you have maybe eyes and also ears to sense what is happening on its body and also around the environment. And then all the informations are clustered into the brain of the bird. And then the brain of the bird processes this information, think about it, what to do with it, and then the brain thinks, okay, I'm going to do this, and then this decision is given to the muscle of the bird. And then the muscle try to move the wing in a certain way to achieve certain functionalities.
Yeah.
So I am mimicking this function of like feel, think, and act, and how to design these algorithms to mimic the brain of the bird to achieve these certain functionalities. Yeah.
So in my mind, you should use a lot of sensors, or how does it work? How does you translate from this bird idea towards the experiment of the SmartX wing?
Yeah. So sensor is actually the contribution of my colleagues. So Roger is working on the sensors.
Yep.
And indeed, we collect the sensor informations, for example, from accelerometers, strain gauges, etc. And then this information is given to a certain control and optimization algorithm. And then the algorithm that I developed is, let's say, based on fundamentals of physics and also first principles, but it is also driven by data. So the data keeps flushing in real time, and based on the real-time data, the algorithm process on it and make certain decisions.
Yep.
How to fly optimally to reduce drag and also to alleviate the loads on the structure.
And what is the time rate of such a change? Is that milliseconds, or is that, or what is needed in flight?
So it's a very good question. Also, we change it in a different time scales. For example, some functionalities like gust load alleviations that you want to shake the loads away if you have encountered with turbulence.
Yeah.
This you have to do it very fast, like in let's say 100 hertz to like 1000 hertz,
Yeah.
depends on the hardware limits. But then for other things like shape adaptations to the environment and also the flight conditions, you can also do it in a slower time scale. For example, in 10 hertz or 5 hertz.
Yeah.
Yeah.
So I think everybody can relate to turbulence, right? So your idea of the morphing wing can solve that solution. But that's what you're trying to say.
I will not say solve the solution, but contribute a little
Make
bit
it
to the
less bumpy ride.
less bumpy, yeah.
Yeah.
Because the problem is that there is evidence shows that with global warming, it's going to get worse and worse. So I don't know, Martin, if you fly very frequently.
No.
Okay.
I think once a year.
I see, yeah.
Yeah.
So there is a research evidence shows that global warming will make it worse, that we will encounter with atmospheric turbulence more and more often.
And why is that, or what is the source of that?
So global warming, you can think there are more energy in the flow, in the air.
Yeah.
And then the energy in the air will make it less, let's say, more chaotic and also more turbulent. Because turbulent is like a dynamics in the air.
Yeah.
So the energy has to go somewhere, so it makes the air more turbulent.
Yeah.
If I'm explaining it.
Yeah.
And then
Right.
that is what you feel. That energy is what you feel if you
Yeah.
sit inside the aircraft. Yeah.
There is statistic data show that aircraft is more bumpy, is bumpier than before. So it is a big, let's say, downside for the passenger comfort.
Yeah.
But at the same time, it is also dangerous for the structures.
Yeah.
Because Roeland has explained, in order to pursue for energy efficient, we have to have like slender wings, so
Yeah.
long and flexible wings. But then this kind of wings is also very sensitive to atmospheric disturbances.
Yeah.
So as you can imagine, like if you have like a glider wing, like very slender, and if there's turbulence, it can really vibrate quite a lot.
Yeah.
So this can also be very damaging for the structures, because structures, you have to be strong enough to resist these disturbances, but also structure can also get fatigue. So
Yeah.
if you just vibrate the structure, like people get very tired, and then, yeah.
Fatigue.
Fatigue, yeah.
Yeah.
Fatigue is like a tiring of the structures.
Okay.
Yeah.
And then eventually the structure will fail
Yeah,
due
fail,
to the
yeah.
fatigue, right?
Yeah.
And that's no. Okay. Everybody can understand that that's not what we want to happen in the aircraft structure. And so if you look at a current aircraft today, do we solve that problem mid-air in turbulence, or is there like some control system working on making the turbulence in flight already less uncomfortable?
Yes. So currently, commercial aircraft has like distributed like flaps and spoilers.
Yeah.
That is connected to the sensors and using. Maybe I'm thinking maybe it's like PID controls or something.
Okay.
To,
Maybe
yeah.
PID control.
Yeah. So it's like a control logic. Like if you get a sensor measurement,
Yeah.
how do you translate what you have sensed to how do you act?
Yeah.
And PID is one of the fundamental control theories that you can do this mapping, let's say, to
Yeah.
decide what to do with the signal.
And maybe, Roeland, if you look at aircraft from 1960s, 70s, like a Boeing 737, and if you look at an aircraft of today, let's say an A350, can you see there's change being made in that 40, 50 years in let's say, morphing wings or adapted structures? Is the wing looks different between these two aircrafts?
Actually, yes. Because let's say at first you would say the wing aircraft didn't change. It seems from a distance.
Yeah.
But indeed, if you look at let's say the 737 wing from the 60s when it was designed, or even a bit earlier, I think, to the A350 wing, we see a few differences. For instance, we see in terms of shape already. At the tips, we see now these winglets that have been used. I mean, many 737s have them as well these days, but
it's an add-on.
It's an add-on, or the new ones have it by default, but let's say the early versions didn't have it.
Yeah.
So now you have this very nicely integrated, continuous winglets on wings. But one example is, for instance, the air brake or the spoiler on the wing.
Yeah.
That's this. Essentially, it's a plate on top of the wing that can be deployed upwards. They can use it in flight, for instance, to slow down the aircraft. Because actually, it's funny that aircraft are so efficient these days that for pilots, if they are in a certain descent towards the airport, and then ATC tell them, air traffic control will tell the pilot to descend to a certain altitude, and sometimes they have to go a bit faster because there's another aircraft crossing or something. That aircraft wings are so efficient that it's sometimes hard to slow down an aircraft in flight. Although you cut the throttle, but if it's descending, so you need more drag with these air brakes.
Yeah.
We also use them on the ground. So if you touch down, you want, of course, to stop as quickly as possible.
Yeah.
So for that, you need a good friction with the wheels. So you want to get rid of your lift force on the wing as quickly as possible. So you also deploy then these spoilers.
Yeah. So if I look out the window in the aircraft, when I touch the ground, I see all these panels coming up. These are air brakes. Yeah.
Yes.
Yeah.
The air brakes, the spoiler, and I mean these have been on aircraft for many years. But what's now the difference with the A350, for instance, is that the air brakes had a certain horizontal position. Let's say flush with the wing.
Yeah.
Just during normal flight, and then they could deploy upwards. But then what happens is the air brakes are towards the trailing edge, so the rear part of the wing, where there's also the flaps. These are these massive. Also, if you land, you see them. They really these, let's say, small wings at the trailing edge that
they extend the wing.
They extend indeed the wing, and they also change the camber, so the curvature of the wing, to make sure you can fly at lower speeds. That you still have the same lift at lower speeds. So if you have these flaps coming out of the wing and deploying downwards and extending a little bit, you create this gap between the main part of the wing and these flaps.
Yeah.
And then the spoiler, now with the A350, cannot only go up for the air brake, but can also go down a little bit now to follow a bit the flow towards these flaps at the rear side or the trailing edge of the wing, and that gives you quite important aerodynamic advantages.
Yeah.
So these are these seemingly invisible improvements.
Yeah.
But so these technologies have improved wing aerodynamic efficiency quite a lot.
And if you look at your Smart X wing, the technology on that wing, on that experiment, when do we see that on an aircraft where we sit in? So when is it going to be in production, I would say?
That's always a very tricky question.
Of course.
Because of course we start at university at low, what they call technology readiness level.
Yeah.
Which means if you start with a crazy idea, that's TRL 0 or 1.
Yeah.
So, and then you go all the way to 9, and 9 means the object is ready for production and be commercialized. So we the nice thing about working at university, of course, is we can think about crazy new ideas.
Yeah.
But of course, our ultimate goal is that, of course, these ideas make it one day to the market, of course, because we want to contribute to a better society, right? That's what we're here for at the university. So our technology now, with the wind tunnel tests and so on, let's say it's now at TRL, so this technology level, we call it 3. So it's proven in a controlled environment, but still with the wind and so on in a relevant environment. And now the question is, will industry pick this up or not to develop this further?
How do we make sure that, let's say, we or the idea is being presented at these aircraft manufacturers? Is there like a meeting where you go as Roeland and say, I have one point on the agenda, I'm going to sell my X-Wing? How does it go, that process of technology being on the aircraft? Do you know that?
We have a few ways. First of all, we know in our respective areas of expertise, we know people at all the research institutes, also at companies like Airbus. We know people are working on these topics as well. So we interact with them. But the best way, of course, to transfer technology is also through projects, collaborative projects. Because in Europe, we're very fortunate that we have very nice research frameworks for also aviation, also in for research also into aviation.
Yeah.
And so there we have worked in quite some projects where Airbus was present, or as a partner, or what they call in the advisory board, where they give comments to look over our shoulder, let's say, what we're doing in these projects with other European partners and give feedback. And that's how they might adopt also technology.
So it's a process of getting to know each other
and collaborate.
Look what's feasible, collaborate in a consortium.
Exactly.
Okay. And that's a long process, I think.
That's a long process because it's also about building trust, for instance.
Yeah.
And that you know that the people who you're working with have the same ideas, philosophy, and can produce good results.
Yeah. And then, Sherry, to start with such an idea of an experiment of the X-Wing, what was the core, let's say, seed that was put in the project when you thought, okay, let's push this project forward? Do you know that, when that moment was, or who came up with the idea of the X-Wing?
I think maybe it's Roland's idea.
Yeah.
I actually contributed to this project at close to final stage.
Yeah.
I was doing my PhD project for another project.
Yeah.
And then once I graduated, I had the honor to contribute to this project.
And
then back then, it's already sort of had the prototype already.
Yeah. What was your spark? What was your... I'm going to contribute on this project. Yeah. What was your interest in the whole project?
I see. So back then, when I look at the wings, they didn't plan to do anything about the control.
No.
So they were actually to demonstrate and also validate the design. That's their main purpose.
Yeah.
And I said, maybe I can do something about this wing to make it smarter. For example, like it can morph, but how can it morph in a different way to achieve certain functionalities? For example, to achieve drag reduction, like how much drag can you actually reduce using this wing. So that sparkles me and makes me excited. So I actually designed an algorithm that can, based on physical fundamentals, but also driven by data. And then we have put the algorithm on the wing. Enable the wing to think during flight, what to do with it. And then we put it in the wind tunnel, and then our experiment showed that we can reduce the drag by around 8%.
80%.
8%.
Oh, sorry, 8%. And you make the wing think.
Yeah.
Is that the part of making a structure smart?
Yes. Yeah.
And then how does it? What's the difference between a non-smart structure and a smart structure?
I think the key is how do you process the data and make smart decisions. For example, the data that is being collected might be identical for like not smart and smart wings. Yeah. But how do you process the data and to make an optimal decision, to think about how to react? That is really the core. So that is translated to how do you design your algorithm, what is the optimal function, what is the constraint, what is the optimalities that you want to achieve, and how do you achieve the real-time capability of these algorithms. That's the key.
Yeah. And that 8%, Roeland, can you translate that into performance, or is it like a liter kerosene you can save on a flight, or how does it translate into efficiency?
That's indeed a key question.
Yeah.
And I'm afraid I cannot answer that question yet, because what we actually do, because indeed we've proven in the wind tunnel that we can reduce the load so much, we can improve drag so much. But then the question is always, because maybe it's very nice on the wing level, but in the end what counts is the aircraft level. And now the reason why I cannot answer this question yet is that we are now doing some research with colleagues from other departments in our faculty on to look indeed at the effect of the morphing and also the smart control technologies on the overall aircraft performance.
Yeah. So the 8% is on the wing, but you need the total system as an aircraft?
Yes.
Okay, understand.
So, and indeed, so it's drag reduction is also weight reduction, because if you can indeed, with this smart control of the control surfaces, you can also reduce the loads on the wing. So this turbulence that we talked about earlier, and that lower loads leads to lower weight, because then you need less mass to absorb the loads, essentially. Again, on the wing level. So then we also have to post-process that on the overall aircraft level, because essentially the energy consumption of an aircraft, so how much fuel or hydrogen or battery power you need on an aircraft, is dependent on drag and on the weight of the structure. These are the type of propulsion. But let's say we focus on drag and weight, these two parameters. And so that's what we're now investigating, these two parameters on aircraft level.
And if you mention hydrogen flight, or maybe electric flight, or battery powered flight, or somewhere in that range, does your design change of the morphing wing when you use a different way of propulsion?
Yes, because let's say the traditional wings, which are filled with kerosene. First of all, then the kerosene is in the wing. That's one. Second of all, you burn the fuel or most of the fuel during flight, so your mass reduces during flight. Not only your total mass of the aircraft, but also the mass distribution. Let's say there's a big difference between, maybe you've seen it also if you're standing on the tarmac ready for takeoff, then the wings are hanging down a little bit, they're bending down a little bit, because there's a lot of fuel in these wings. And then you take off, so you see the wing flex up a bit, of course. But then at the end of the flight, let's say, certainly if it's a long distance flight, there can be more than a meter or a few meter difference in deflection by the time you arrive. And this change in mass also has a big implication on the loads, for instance, and so on, and the control system. If you would fly, for instance, with batteries, of course, you consume their energy, but batteries don't change their weight.
No.
So then you have this weight which is constant over the flight. So that's different than a changing mass over a flight. And then the third thing is that, for instance, with hydrogen, I'm not a hydrogen expert, but what I've seen is that most likely hydrogen will be stored more in the fuselage rather than in the wing. So then all of a sudden you have a wing. Then still the aircraft changes mass because the hydrogen is still consumed during flight. So the mass reduces, but the wing mass will not change in this case. Because now at the moment kerosene is in the wings, but the wings are going to be what they call dry wings. We call it. So that also has different implications for the aircraft, for the wing design.
So it's part of the system of the aircraft.
Yes.
The design. So often in society, if people see change, they want to pull you back into something they already know, right? And if you look at the university, especially at the aerospace faculty, we do weird stuff if you look at from the outside in. How hard is it to maintain that level of curiosity, or being always on top of the innovation?
Well, okay. Let's say in terms of ideas, we have the luxury that we can indeed think freely. So, and that you are more than welcome to indeed have ideas that people might not believe in yet, but that you're convinced. So I think it's actually very important as a researcher or professor at the university to have a vision, and to stay also loyal to that vision, in spite of maybe sometimes people saying it might not work, but you say, no, I have a vision, I will prove to you that it will work. And we also have to accept that proving that something doesn't work is equally valuable than proving that something does work.
Interesting.
Because sometimes often we read a lot of success stories, right, on LinkedIn, in papers and so on. But behind every success story, there are maybe 10 ideas that didn't make it.
No.
And that's fine. That's actually coming back to this technology readiness level, we're at the low technology readiness level. So we have I call it luxury, and also challenge at the same time to come up with ideas that might not make it, because maybe for every idea that made it to an aircraft, there maybe are 50 ideas that didn't make it.
What are the next steps of control of making the wing smart in your field of research?
Oh, that's a very interesting question. So I think so far the wing is far from as smart as a bird, or not as far as smart as like a human.
Yeah.
So there is still a long way that we can go. For example, I'm also exploring the learning perspective, like how let's say the algorithm can learn from the past experience and also collect data from the environment. So not only data from itself, but also environment, but also data from the environment, and also data from the past, learn from its past experience, and become smarter and smarter.
And what is the? You said it's a long road. What is the first step? To measure more, or to do you still use the SmartX as a platform, as an experiment to conduct that thought?
Let's say not necessarily. Let's say the first step might be that I build a simulation environment. Let's say like a digital twin of that SmartX wing.
Yeah, maybe it's good to ring the bell as to explain
twin,
digital twin. Yeah.
Digital twin is like the copy of a physical thing in the digital world.
Yeah.
Yeah.
So you can change it in the digital world.
Yeah, you can do crazy stuff in the digital world that you cannot do the smart wing.
That's true. That's true for every every field of digital worlds, right?
Yeah.
And one thing pops in my mind. It's AI, of course, hot topic. Do you use a lot of artificial intelligence in your research, or is it becoming more and more? Some.
Yeah, I always believe that the hybridization between like physical foundations plus learning is the way to go.
Yeah.
If the learning doesn't have any physical foundations, I mean, maybe by chance you can get it right, but then the chance is really low. I have actually tried some like a model-free learning algorithm on the SmartX morphing wing. It's one of the examples that it fails.
Oh, really?
Yeah, it doesn't really work. So it has to have some understanding or interpretations of the physics. Otherwise, you need massive data to learn about it.
And what failed, in your opinion, doing that small experiment?
For example, like you have certain objectives that control should make the wing alleviate some of the structural loads. But then maybe the control is doing some random crazy stuff. Maybe in the simulation environment, it works pretty well. But then if you apply it to the real aircraft or the real SmartX wing, it starts to do some crazy stuff. This is the bottleneck that we phrase it as the simulation to reality gap. Because reality, you have so much uncertainties. The model is not, let's say, the ground truth, and the model can be different from day to day. And then the environment can also be time varying. For example, the temperature, the density. There are just so many factors that you cannot model everything in the simulation environment.
And also with the growth of, let's say, the maturity of artificial intelligence, do you think that this experiment will succeed in 2 or 3 years, or in the near future? Or is it still based on the fundamentals of physics that's needed?
That depends on how do you define succeed.
That's true.
Yeah.
Maybe you can define what you think is a success in that part.
I think actually, let's say for aviations, I think safety is always let's say foundation and also the bottleneck.
Yeah.
Without safety, we cannot talk about sustainability. We cannot talk about smartness, adaptations. So, in my opinion, like this model-free learning can never be 100% safe that people can trust to step into it.
Yeah.
So. And it needs massive data and also training and resources to make it right.
Yeah, and are we producing not enough aircraft to do that, or?
No, I think the key is really the physical, let's say, first principles, the physics.
Yeah.
You should have, the algorithm should have the certain understanding of the physics and also obey to the physical laws. For example, Newton's second law.
Yeah.
You should obey this law to make the algorithm work.
Yeah.
So the physics is really the core around it. And then the data-driven can make it a little bit better, but without a model, without the physics, it might work, but it's not guaranteed.
No.
It might be very risky to step into the aircraft like that.
And that part that it's not guaranteed, that relates to safety directly, and then we don't do it.
Indirectly, let's say.
Yeah, indirectly, yeah. And if you have the complete freedom in your work, what would be the next step in your research? Without any boundaries, just to dream big or to dream to the next step? What?
Yeah, my vision is actually about like smart adaptive structures. Let's say not only aircraft, but it can also be like wind turbine blades, maybe some underwater structures. So my idea is actually also inspired by how birds fly.
Yeah.
So let's see, if you observe the birds, if there's turbulence or if there's gust, the bird doesn't just stand still and strongly resist the disturbance. The key word is about adaptation.
Yeah.
How can you adapt to the environment? How can you make use of the environment to do something, to get benefits from it?
Yeah.
So this is a fundamental paradigm shift to change flexibility from something that we want to avoid to something that we can explore and make use of.
Yeah.
This is really the dream that I want to achieve.
Yeah, nice.
Yeah.
So it's funny because I if I think about, let's say, 150 years ago, before we even could fly, that people also looked at birds, right? They were wondering, how can we as people fly? Let's look at nature. Mm-hmm. And then maybe we turned into technology. And then now we're transferring back to, let's say, to look back at nature again, how they do it. Is that a good observation, or what do you think?
I think along the way, people is constantly looking at what we can learn from biology.
Yeah.
Let's say it's not, cut it in the middle or something.
No.
Like as a researcher, we constantly look at what we can learn from biology.
No.
But it doesn't mean like aircraft is worse than bird or something.
No,
because we fly much faster than a bird, right?
Yeah.
We achieve that, and the bird can never fly above like Mach 0.3 or something. So we actually is better than our aircraft is actually better than bird in some aspects.
Yeah.
But there are still so many things that we can learn from biology, from birds, from insects, from butterflies, or maybe there is some feature called flying squirrel.
Yeah.
So this kind of animals, we can learn so many things from it. So it's not necessarily we are going to make an aircraft that looks like bird.
No.
But actually, some aspects of the birds can be translated to our current aircraft, or maybe the aircraft of the future generations, to make it smart in some aspects.
Yeah. And Roeland, talk about vision. You're the fresh new chief of ASM of the ASM department. What is your vision?
For the whole department, you mean, or for my own research?
Or both. Or I think they're a bit intertwined, right? So
true.
Yeah.
I'm a very strong believer in multidisciplinarity. Yeah. To really try to combine disciplines as much as possible to make the next step in efficiency of aircraft structures. Because, I mean, aircraft structures at the moment are already incredibly efficient. They went through decades of optimization, essentially, right? So, and multidisciplinarity is already embraced, because an aircraft by default is a multidisciplinary
machine. Yeah.
Where you have to make trade-offs between aerodynamics, propulsion, structures. Don't forget the passenger experience.
Yeah.
It's also important.
Yeah.
But I think we should go still one step further, and that's really my dream, to one day. That's really a dot on the horizon.
Yeah, sure.
To be able to. Because now, if we're still designing aircraft at the moment, still the disciplines of aerodynamics, structures, and so on, and control are quite distinct, so to say. Yeah?
They're different departments.
Different groups, indeed.
Yeah.
And of course, there are very good reasons for that at the moment. And the way that aircraft manufacturers made their aircraft is really impressive. But if you could still remove these disciplinary boundaries, to go to really multidisciplinary designers, engineers, then we can still improve the aircraft further.
To conduct this episode, I prepared 3 statements, and you can react on it. Sherry, for you, if you have to choose between doing research or teaching, what do you choose?
Can I choose both?
No.
Well, I actually really enjoy teaching because I feel it's really rewarding to interact with students. And this fresh mind has very sparkling new ideas. It's really inspiring talking to them.
Yeah.
But at the same time, I also like research very much. I enjoy the freedom that you can dream, that you can explore. And if something works, it's not the end of the world. You can just communicate to people that it doesn't work and why it doesn't work.
Yeah.
So yeah, if I have to choose, maybe research.
Okay, and for you, Roeland?
I think my answer is going to be roughly the same as Sherry's.
Yeah.
That I really like interacting with young people. That's actually the beauty of also working at the university. You can interact with the next generation of researchers, of engineers, and so on. So it's really nice to interact with them. And I would still dedicate quite some time on that, but the research is... but, okay, I know I have to choose, but still I would like to make one statement that
Sure.
in the university, research and education are also intertwined. That's actually the beauty about a university specifically. And we do research, and actually our research is also a vehicle to teach people, because there is, of course, a lot of textbook knowledge that we also need to convey to the young generation. But with our research, which should be hopefully state-of-the-art, we can also use that research to teach people.
Yeah.
And there are different ways of teaching it. There is the classroom lectures, but let's say there's also the project education and the master thesis, for instance. That's also part of teaching. And for sure, in a master thesis, there you see research and education
hand in hand. Yeah.
Indeed.
Yeah. Thanks. Second statement for both is it's about technology. Do you think, Sherry, that the technology is already here? Do we have enough technology, for instance, on the Smart X-Wing? Or you say, no, we need more time and effort to do more research?
I think it's never ending. There is always something interesting, something new, something you want to explore. It's it's never the end of the story. We can have the next generation of the aircraft, the next generation of the aircraft.
Yeah.
And the research goes on and on, and together with technology.
Yeah. Okay. And for you, Roeland?
I agree also here with Sherry.
Yeah, that, that's okay.
I think research is, by the way, very important, because sometimes I have the feeling that there is a tendency to think that ideas and technology is there, but it needs to be developed, right? So we still need to invest in also the fundamental research. And I think with every answer you give to a question, you have maybe 10 other questions.
Yeah.
Let's say if we developed, as humanity, developed the heavier-than-air-powered flight in 1903 with the Wright brothers. That was a huge breakthrough. But then the next question came, okay, how do we scale this up? How do we make it more efficient? Yeah. Because now aviation has grown so much, so the question is now, how do we keep flying without environmental impact?
Yeah.
So every new invention comes inevitably with maybe 10 new questions.
Yeah, interesting. Last statement for you both is... I do so not fly at all or fly consciously.
That's interesting.
It's a personal question, maybe.
Yeah, I always dream that I can have like the arbitrary door, like a magical door. Like just open the door and I go to anywhere in the world without damaging the environment or
like
something.
Teleportation.
Yeah. I will choose the second one because sometimes maybe I have to see my family. Yeah. I have to see my friends. Yeah, but I try to fly less and less.
Yeah. Okay, thanks.
Yeah, flying consciously.
Yeah.
For every flight you might take, you have to really to ask yourself, should I fly? First of all, should I travel to another location, yes or no?
Yeah.
And if I do that, what's the best means of transport?
Yeah.
And it doesn't always have to be fast and tomorrow or today already. You can also take maybe a few more days to travel and so on. So, but flight really connects the world.
Yeah.
So, and I'm a strong believer in if people meet each other, it might resolve a lot of problems. So I'm really a strong believer that meeting people is very important, and flight is part of that ability as humans to meet each other. But indeed, ask yourself always the question, should I fly now and should I fly at all? But if that's the best option, then yeah, you can do it.
Yeah. Thanks.
Yeah.
Thanks, Roeland. Thanks, Sherry. You want to add something more?
Yeah, I think flight is very important to connect people as one means of transportation.
Yeah.
But I hope with the technologies that we're developing, flying can be more sustainable in the future.
Yeah.
And maybe in the future we can also have hydrogen powers. So let's say it's less contaminating to the climate.
Yeah.
And also with maybe air traffic management, we can try to solve the control of the aircraft thing.
Yeah.
And then let's say compare flight with ground, underground, let's say not underground, but also underground transportations like cars and trains,
Yeah.
and also maybe public transport. It's not necessary
Yeah, I understand.
worse
Yeah.
than that,
Yeah.
in my opinion.
Yeah.
Yeah. So I think people should be very smart about when to travel and how to travel. But then I don't think we should just stay at home and do not get physical contact with each other anymore.
Yeah. It's important.
Yeah.
Thanks for that.
We're trying to indeed make aircraft more sustainable,
Yeah.
aviation more sustainable, that people can keep flying if they really have to, of
Yeah.
course.
Yeah.
But yeah, that's our mission essentially.
Thank you both for this interview.
You're welcome.
Yeah.
It was a pleasure.
Thanks, Sherry.
Thank you.
Aviation doesn't change overnight. It moves through decisions, trade-offs and time. And maybe the real question isn't how fast we can change, but how consciously we choose to. Thanks for listening to Coffee with Martin, and tune in for the next episode.